Hi, my name is Aaron Fries. I'm the NASA LPDAC Science Coordination Lead, and I'm here to talk to you today about getting started with Earthdata Cloud. As you may know, NASA is migrating its data archive to the cloud. Not only its data, but its websites, services, and NASA applications are also being migrated to the cloud, specifically in AWS Cloud Region US West 2. Why is NASA migrating to the cloud? This is primarily driven by the expected large data volumes being produced by NASA missions in the near future. Not only are the data volumes large, but we are experiencing an increase in the types of data products we offer. This large variety of data include data like modeled or simulated data products, aerial imagery, LiDAR data products like point clouds or full waveforms, and numerous products derived from optical and SAR sensors flying on platforms orbiting Earth. The cloud will allow data archives to overcome storage and distribution bottlenecks. It will allow data users to overcome processing bottlenecks, allowing them to process Earth observation data at scale or whatever scale they want. Finally, NASA migrating data to the cloud means putting authoritative data next to compute. Here's a schematic of the Earthdata Cloud paradigm. DACs at the moment are migrating their data to the cloud. NASA Earthdata Cloud will not just contain data, it will also have metadata records associated with those data archives, as well as enterprise tools and services that will be able to be leveraged to do anything from searching and discovering, visualizing, subsetting, and transforming data. Data users will be able to pull data out of the cloud to perform their analysis or move their analysis to the cloud to work next to the data. As NASA transitions to the cloud, so too are NASA data users. What we see here is a traditional download and analyze model versus the cloud model of analysis in place. With the download and analyze model, users are working within a stovepipe, accessing and downloading data from individual DAC archives using DAC-specific catalogs, services, or APIs to acquire the data they need. In this model, users are downloading data, which is inefficient and requires resources to store these copies. This model does not scale well in an age of big Earth observation data. The cloud analysis in place model is much more efficient and scalable. With NASA data and metadata in the cloud, users can find data across multiple archives and perform their analysis next to the data without downloading. Users are able to use cloud-based work environments like Jupyter Hub, where users can perform their analysis using common APIs and services to find their data, and open source scientific compute libraries like Xarray to read data, Dask for parallel processing, Rasterio for geospatial raster processing, and HoloViz for interactive visualizations, to name a few. This allows users to do their analysis without the overhead of downloading and managing data to their local machine. Further, working in the cloud gives users the opportunity to leverage cloud resources to scale their analysis to perform bigger, faster, and more efficient analyses. For the remainder of this time, we'll talk about getting started with the Earthdata Cloud. There are a few different categories we can talk about when discussing getting started. Things like search and discovery, downloading and accessing cloud data assets, and processing those cloud data assets both inside and outside the cloud. Today, we're going to focus on search and discovery and download and access. On the search and discovery front, users can use a graphical user interface to search for cloud data assets, something like Earthdata Search, or users can programmatically search for these assets using APIs. Earthdata Search is an enterprise web application designed to search and discover data assets across all NASA EOS DIS archives. It has numerous capabilities for filtering and narrowing in on desired datasets, things like faceted search for categories like platforms or data providers, as well as spatial and temporal search constraints that allow users to narrow their search criteria to certain areas and/or time periods. Here we have an example of doing a basic search using the search bar. I type HLS, which stands for Harmonized Landsat Sentinel, a collection that's hosted in the cloud by the LPDAC. Now doing this will return any data collection that is either on-prem or in the cloud that is related to HLS. Note the 6 matching collections. If I'm interested in only cloud data assets hosted in AWS, I can go to the Filters collection and select Available from AWS Cloud. This will return only collections that are hosted in the cloud. Note the 4 matching collections we now have. After selecting one of the collections, in this case HLS S30, I'm presented with all the granules available for this collection. I can use a polygon search capability here in the right to draw the feature on the map and constrain my search results to granules that intersect with that feature. If I determine I only want a single granule, I can download that by clicking the Download button, which then gives me 2 options for accessing these data. Option 1 is to download the data, where in this case our granule consists of multiple cloud-optimized geotiffs that can be downloaded separately to my local machine. Also available under the AWS S30 Access tab are the S3 links to each asset for in-region direct access from the cloud. These links aren't used to download data, but provide access to the data such that users are able to do their analysis next to the data, specifically from within AWS region US West 2. If instead I have to download multiple granules for my project, I can add these granules to a basket using the plus sign found at the bottom of each card. After selecting the desired granules, users can click the green download button, where again they'll have 2 options for downloading or accessing these data. Note that this path adds all downloadable data assets to the list, one that can be downloaded and one that has the S3 links for the in-region direct access. So now we've covered the graphical user interface option for discovering cloud data assets. NASA also has a couple programmatic ways of doing the same. These include the CMR Search API, or the Common Metadata Repository Search API, or the CMR STAC API. Both the CMR Search API and the CMR STAC API can be used from various command line download utilities like curl or wget, or these APIs can be used from a preferred scripting environment. The CMR Search API is quite robust and is capable of delivering metadata across all EOS DIS data assets. I encourage you to explore the CMR Search API link provided here if you're interested in using that specific API. In this talk, we're going to focus more on the CMR STAC API and how it can be used to search for and discover cloud data assets within EOS DIS. Before we go into the CMR STAC API, we're going to take a step back and learn a little bit about STAC. STAC stands for the Spatiotemporal Asset Catalog, and is an open specification that provides a common language to describe a range of geospatial information so that we can easily index and discover geospatial assets. The STAC specification is made up of 4 loosely connected specs. These include STAC catalogs, STAC collections, STAC items, and STAC API, where catalogs provide a way of structuring and organizing STAC objects. Collections provide a way to group items based on shared characteristics. Items are the individual spatial temporal objects that contain associated geospatial assets, and the API enables searching of those items. The CMR STAC API is an implementation of the STAC API spec. It acts as a translation layer converting CMR metadata to STAC. Here we have an example of the CMR STAC API endpoint on the left. It contains links or the entry point to all EOS DIS data provider archives. The example on the right is of a STAC item. This contains geospatial, temporal, metadata, and links to data assets. Items are also valid GeoJSON features. So with the CMR STAC API, a catalog maps to what we would typically think of as a DAC or provider archive. We could think of the STAC catalogs as the data products one would find within a DAC or provider archive. The STAC items would map back to individual granules, which also contain the data assets or files users want to download or access. As it's always been, data can still be downloaded. And regardless of whether users are downloading the data from the cloud or accessing the data in the cloud, the data is still provided at no cost to users. Users can also remotely access data from the cloud from a scripting environment like Python and R. Here we demonstrate how to read in a download link, specifically the HTTPS links, for an HLS cloud asset. We're doing this within a Python Jupyter notebook. Because the HLS data are stored in a cloud-optimized format, we can efficiently read in a portion of the original file into the notebook using the clip routine, which drastically speeds up the read operation. In addition to reading in single files, we can also read in multiple files to build a data cube of sorts. Here we demonstrate how to build a time series for the red band within an HLS collection. On the right, we demonstrate what you can do with the data once it's in Python, specifically in an XArray data structure. Here we demonstrate how to calculate an enhanced vegetation indices layer using the red, blue, and near-infrared bands from the HLS data collection. This kind of operation can just as easily be applied to the time series data cube like the one on the left. In the previous examples, data was read into a Python environment using the HTTPS download links for each cloud data asset. Cloud data assets also have an S3 URL that users can leverage for in-region direct S3 access. This means that the user can work within AWS region US West 2 and access the data without downloading. But not only that, users who've moved their analysis workflow to the cloud have the might of the AWS cloud at their disposal to scale their workflow like they would likely never be able to do from a local machine. Data access routines for direct S3 access remain the same, except that users must submit temporary S3 credentials, which are generated via a request to a NASA service. Again, data that can be read in as a single file, users can build time series data cubes as well, and really whatever the imagination can come up with. We know this is a dramatic shift in the way users can work with data. We think that the new cloud paradigm will allow users to really leverage Earth observation big data in ways not possible from local work environments. To help transition scientists to this new paradigm, NASA has teamed up with Openscapes to help develop skill building and community engagement approaches for transitioning science workflows to the cloud. Through this collaboration, the EOS DIS DACs are coordinating to develop learning materials to help science transition to the cloud. We recently completed our first Earthdata Cloud Hackathon. We are also creating and organizing materials we developed into an Earthdata Cloud Cookbook containing code examples, tutorials, and more. Please follow the links if you're interested in learning more. Thank you for listening to this presentation on getting started with Earthdata Cloud. Here are a few resources that you can follow that will help you get started from your own environments with Earthdata Cloud. Thank you.